At the end of the 18th century, Antoine Lavoisier, with the assistance of his wife, Marie Anne, and others, laid the true foundation of chemistry. The first experiment was simple. Weigh a bit of metal. Bake to powder. Weigh again. The powder will be heavier than the bare metal by the amount of oxygen combined with it. Lavoisier's before and after weighing is still the first method of chemistry. Every lab has an analytical balance or two. The most basic chemical processes are oxidation, reduction, and reactions with acids and bases. Before Lavoisier, there was no firm understanding of these processes. Here are some examples of experiments. 65.38 grams of zinc is baked to a powder. Then, when reweighed, the powder weighs 16 grams more, or 81.38 grams. Now we would say that an atom of zinc of atomic weight 65.38 is oxidized by an atom of oxygen of atomic weight 16. Hundred 162.76 grams of zinc oxide powder heated with 12 grams of carbon leaves 130.76 grams of zinc and releases 44 grams of carbon dioxide. Iron heated with air produces one of several oxides. The oxides have different colors depending on the temperature and presence of water. In the tempering of steel, the oxide colors from light straw to blue relate to the softness of the steel. Steel is let down to blue to soften it before machining. Iron oxide heated with carbon produces iron and carbon dioxide. Hydrogen heated with oxygen produces water. The reaction is explosive. Hydrochloric acid combines with sodium hydroxide to form sodium chloride and water. Acids also react with metals. Hydrochloric acid reacts with zinc to form zinc chloride and hydrogen. The main work of the 18th and 19th century chemist was weighing things before and after a reaction. By doing thousands of such experiments, patterns became obvious. Finding the atomic weights of elements and the structure of compounds from these experiments was a puzzle to be solved from these patterns. The balances built by Meunier and Fortin for Lavoisier were the marvels of his laboratory. Nicolas Fortin was the instrument maker who built the first metric weight standards, a work of tremendous delicacy. Mechanical balances are seldom used today, being replaced by electronics, but as tools to illustrate concepts, they are invaluable. Work with a balance makes a lot of mathematics, physics, and chemistry immediate and visceral. While electronic scales are cheap and easy to use, they don't give this feel for the work. I decided to try building a crude balance using hardware store things. Aluminum for the beam, hacksaw blades for knife edges, and so on. Here's the balance that I've constructed. It's deliberately crude because I want you to feel that you could do a better job than I have. It illustrates most of the principles of the balance, though. You can move this dime across. To reach equilibrium. Not essential for weighing. You have hacksaw blades for the knife edges, here, here, and here, and some sort of a stand. The only part that's a little bit odd are these bolts, but by putting bolts in, the bolts are designed to raise the center of gravity. The center of gravity of this beam is actually low because these pieces extending out. And if you get the center of gravity, if you get the 3 points here on the line of the center of gravity, it gives you maximum sensitivity. The sensitivity of the balance is not that great. And of course, if you were building a real analytical balance, there would be several things you would have to do. There would be a fork which raised this up. So you could put your trial weights on, then lower it down, see where it went, raise it up. There would be an indicator of some sort. Sometimes they would put a pointer out here to a scale behind here. Sometimes they would have a little telescope with a reticule on it, or a little microscope with a reticule that aimed. You'd also have to have it in a case. You can see the wind is causing it to move quite a lot. And you can't have that, of course, when you're trying to weigh something accurately. As the electronic analytical balance illustrates lots of basic technological principles, it might be interesting to build an electronic analytical balance, or at least to see how it might be done. The heart of it is the coil and magnet. The position of the beam and magnet is controlled by an analog system with an optical position sensor, amplifier comparator, and voltage to current converter. As weight is added, the position sensor's voltage changes, giving an error voltage between it and the fixed reference. The amplifier sends the amplified voltage error to the voltage current converter, increasing the force from the coil and pushing the sensor back toward equilibrium. The result is that the pan moves only a tiny bit, and the weight is proportional to the amplifier voltage. The amplifier voltage is read by a computer that scales the value, averages it, and controls the display. Here is the addition of the computer. The tare button zeroes the display. The cal button sets the scale factor when a reference weight is placed on the pan. Here Here's a little more on the slot and vane position sensor. You have a vane that moves up and down, and a slot. Here's no light getting through, here's full light, and in there be about half. So by adjusting the amount of light with the slot and vane sensor and comparing it to a reference standard for half light, you can hold the weight at the exact same spot at all times. So it gives you full light, half light, no light. A very sensitive way of measuring distance with a light meter and an LED. Every modern scientific instrument has a sensor and a computer. The sensor is connected to the computer by an analog circuit, which can be a simple amplifier or, as in the balance, a control system. The computer part of an older instrument is usually not repairable or expandable. Old computers are always a problem. If they quit, they're junk. The analog part is usually easy to fix and is the heart of the machine anyway. Most of the analog chips are still being manufactured. The fancy computer is often really a simple display and interface manager that can be replaced with just a little programming. Arduino to the rescue. It is hard to overstate the importance of the late 18th century chemical research. A century before Lavoisier, Newton made great strides and in many respects structured the modern world. But Newton was an alchemist, boiling mercury and seeking spiritual results from the arcana of Hermes Trismegistus. For Newton, the four elements were earth, air, water, and fire. For Lavoisier, they were hydrogen, oxygen, carbon, sulfur, and about 60 other substances. Now, the pioneering work of Lavoisier would merit the highest prizes awarded to an elite group of researchers supported by grants from government and industry. The realm of science is not valued by all, however. There is a dark current in society of jealousy and passions nursed by those who don't understand the scientific process and fear technology. A horde of poorly educated people who believe science is the evil realm of madmen and who jealously equate intelligence with malice. American anti-vaxxers who don't know that George Washington mandated vaccinations at Valley Forge, an act that made the United States possible. People who, with no evidence, believe life was somehow better in the 7th or 13th century. People who ignore the plagues in the 6th and 14th centuries. People who, with no evidence, believe they know more than the rest of us. People who think they can figure things out better with no use of mathematics. I'm sure that science is the key to human comfort and survival. Knowledge can solve all our problems if the anti-science mob doesn't grow too powerful. So speaking of an anti-science mob, here's the story of Lavoisier. Lavoisier was an aristocrat and philanthropist who financed all his own research. He equipped the best laboratory in the world at the time using money got by taxing tobacco. He improved the regulation of the tobacco trade. When the revolution came and the mob was killing aristocrats, Lavoisier's regulation efforts were considered graft. He was put on trial before an anti-science judge and guillotined. It is fitting that the judge himself was guillotined 3 months later. It is also almost fitting that the government eventually issued an apology and returned Lavoisier's confiscated possessions to the bitter Marie-Anne. It is fitting that we honor the memory of two of the world's geniuses, Antoine and Marie-Anne Lavoisier.